Alright, so this is our AP Chemistry lesson video for Chapter 17. This is part 2, and in this video I'm only going to cover section 17.3, but it's literally just going to be like the full length of an actual movie you would go see in a theater. But instead of watching something super exciting, you're going to watch me do a bunch of math with titration. So keep in mind all the math that you're about to see me do in this section. This is from the textbook. Okay, on the AP exam, you will not see a bunch of this long, extended math because you wouldn't have time to finish it. Okay, but I'm still going to go over it because this is also to prepare you for college, and so at the college level, who knows what your teacher's going to want you to do. Alright, so I will try to make this video as painless as possible, but it's going to be pretty painful. So let's go ahead and get started. Wasn't that an exciting opening to this video? Alright, so we're going to focus on acid-base titration. So in other words, we are adding an acid to a base until we reach equivalence point, or we're adding a base to an acid. Either one could be strong or weak. So acid-base titrations have two important points. You have the equivalence point and the end point. So the equivalence point is the point at which stoichiometrically equivalent amounts of acids and bases have been added. So you have the same number of moles of acid and the same number of moles of base that are in your beaker or flask at that point. The end point is the point at which the indicator changes color. A good titration, those 2 points should happen at about the same time. So a titration curve is a graph of the pH as a function of the volume of the added titrant. Okay, so here, for example, I can see I'm starting with a 0 pH, so that means clearly I'm starting with an acid, and then as I add base, my pH starts increasing. Once you get to halfway up this vertical line, that is your equivalence point. That's when your moles of acid equal your moles of base. If you have a strong acid and strong base, equivalence point will be at 7. And then after equivalence point, you can see pH continues to increase as you add that base. Alright, that's what it looks like for strong. So notice it's a nice, crisp S-looking curve. When you titrate a weak acid with a strong base, your pH, notice it's going to start a little bit higher, and then notice the shape. Here we have this nice S curve happening. Here it's kind of like, okay, I'm trying to be an S. Okay, so it kind of messes up the front because the thing is, right here you have a buffer because you have some weak acid in its conjugate base, and so that's why pH changes a little bit differently than it does with strong and strong. Notice at the equivalence point we are actually higher than 7. And that's because this is a weak acid. So every time you neutralize a weak acid, you're creating its conjugate base. So that's why at the equivalence point, it's greater than 7, which is weird for people to understand because they think, well, if I have moles of acid and it equals moles of base, then how in the world is it not at 7? Well, because as you're neutralizing that weak acid, you're also making its conjugate base. All right, but then the end of the curve ends up looking exactly the same because it's just the strong base that you're adding. And then also notice that vertical area is much shorter for a weak strong than it is for a strong. Again, that's because of that whole buffer region that occurs. Alright, so there are 4 important points in a strong acid, strong base titration curve. So we're going to start with strong. So what we're going to talk about is this type right here. So there's 4 important points. The initial pH of the solution is determined by the H+, because it's just a strong acid or strong base. Between the initial pH and the equivalence point, the pH is determined by the amount of acid not yet neutralized. So we can ask about this point here. We can ask anywhere in this area. Next is the equivalence point. For a strong acid, strong base, that's super easy. If they ask you what the pH is at equivalence point, if it's strong acid, strong base, it's going to be 7 because your moles of acid and base will have neutralized one another. And then after the equivalence point, the pH is determined by the amount of excess base. So they could ask you the initial, they could ask you somewhere between initial and equivalence, they can ask you equivalence, which for strong is just 7, or they can ask you anywhere after the equivalence. Alright, so let's look at some math together. So the math is going to be excessive and long. I apologize, but I will try to make it as fast as possible. So it says calculate the pH when the following quantities of 0.1 molar NaOH, so that's a strong base, solution have been added to 50 milliliters of 0.1 molar HCl, that's a strong acid solution. Alright, so I know I have strong. I can clearly see that since the molarities are the same, the equivalence point would be at at 50 milliliters. Okay, since both of the molarities are the same, the volumes just need to be the same. So in other words, what they've asked me is right before the equivalence point and right after the equivalence point. So what I need to do is I just need to figure out, okay, well, what has reacted, how much excess acid or base do I have? Once I know that, because it's strong, I can just use my pH square formulas to calculate pH. All right, so let's start with our 49 milliliters. All right, so here we have 0.1 molar OH minus, okay, because remember there's just one OH here, OH minus times, and I have, let's see how much of my NaOH, 49, so 0.049 liters. All right, so once I multiply that, I can see that I have used 4.9 times 10 to the negative 3 moles of OH minus. All right, so that's how much OH minus I've used, because when we're trying to do neutralization, we have to compare moles. All right, so then I do the same thing for my acid. So I can say, okay, well I have 0.1 molar of H plus, because there's only one H here, times, and I have 50 milliliters, so 0.050 liters. And I got 5 times 10 to the negative 3 moles of H plus. So obviously I can see I have more moles of H plus than I do OH minus. But 4.9 times 10 to the negative 3 are going to be neutralized. So I just take my larger amount and subtract my smaller amount from it. So I say, okay, well 5 times 10 to the negative 3 moles of H plus minus what's going to react is 4.9 times 10 to the negative 3 moles of OH minus. That's going to leave me with excess 1 times 10 to the negative 4 moles of H plus left over. So this is what's left over. This is what has not reacted. Okay, however, they didn't ask me that. They asked me what's the pH. So this is where you have to be careful, because right now we have moles. We know that to get pH, it's negative log of the concentration of H plus. It's not the moles of H plus. So we need to change moles to molarity. All right, and that's a step that a lot of people forget. So we have 1 times 10 to the negative 4 moles of H plus. So then what volume are we going to use? Okay, well, are we going to use 49? Are we going to use 50? We're going to use neither of them. We have to add them together. So remember, what we have done is we have added this base to this acid. And so as we add the base, the volume increases. So we actually put total volume on bottom. So it actually ends up being 0.099 liters because I combined the 50 and the 49. All right, and so once I get that, I got 1.01 times 10 to the negative 3 molar for H plus. So now I can plug that into my formula. So it's negative log of 1.01 times 10 to the negative 3 molar, and that gives me 3.0. So that's my pH, which makes sense because we haven't neutralized all of the acid yet, so it makes sense that it's acidic. All right, so now we're going to go after the equivalence point. So I can already tell, okay, now I have passed when they're equal, so now there's more base. So at this point, I would expect a pH higher than 7. Okay, so let's look at this one together real quick. I say real quick, these aren't even the long ones, and you can see how long they're taking. The weak ones are the long ones. All right, so we have 51 milliliters of NaOH that we're adding. So I start the same way. I said, okay, I got 0.1 molar OH minus times, in this case, 0.051 liters. And I ended up getting 5.1 times 10 to the negative 3 moles of OH minus. Now, I can use my same acid value from up here. Okay, I don't have to recalculate that. I still used 5 times 10 to the negative 3 moles of acid because that's what was already initially in the beaker or the flask. All right, so I don't have to recalculate that. I do still need to subtract. This time I have more base than acid, so I do 5.1 times 10 to the negative 3 moles of OH minus, minus 5 times 10 to the negative 3 moles of H plus. And so what that does is it tells me I have 1 times 10 to the negative 4 moles of OH minus that's left. So this is left over. Okay, but remember, to get pH, I need concentration. This is just moles. So I divide again by the total volume. Okay, so I have 50 and 51. So I divide by total volume of 0.101 liters, and I end up getting 9.9 times 10 to the negative 4 molarity of OH minus. Alright, but it didn't ask me for molarity of OH minus, it asked me for pH. But I have to be careful. I have OH minus. So if I do negative log of this, I'm going to get POH, and then I would need to do 14 minus. Alright, so I do POH is negative log of 9.9 times 10 to the negative 4, and that ends up giving me 3. But I need pH, so pH is 14 minus 3, which of course is 11. Just like that. Alright, and so be careful, like if you got 3, it should mentally make no sense. You have now added more base than acid, and it's strong, strong. So it should make no sense for pH to be less than 7, because at equivalence point, it's 7. Alright, so hopefully that wasn't too bad. We actually did one similar to this in honors. You probably have forgotten by now, but it happened. Alright, so let's let you try one. Alright, so, gosh, of course there's A and B. There's so many A's and B's too on these, y'all. I'm so sorry. Alright, so I'll assume you pause it, try this one, and we'll look at it together. So it says calculate the pH when the following quantities of 0.1 molar HNO3, so I know that's a strong acid. Right now, I know it probably seems like a waste for me to write strong acid and strong base, but remember on the AP exam, it's not like there's a section where you know it's strong, strong, or weak, strong. So I always like to label to make sure I know which one I want. Alright, so we have the following quantities of HNO3 have been added to 25 milliliters of 0.1 molar KOH solution. So that's the strong base. So I know it's strong, strong. So this time I'm starting with a base, so I should be starting with high pH. I'm adding an acid, so it should lower as we go. Alright, so I can see that the concentrations are equal, so that means at equivalence point I would be at 25 milliliters. So they have asked me slightly before and slightly after the equivalence point again. Alright, so let's go ahead and get started. So for this one, I said, okay, I got 0.1 molar of my OH minus times 0.025 liters, and I got 2.5 times 10 to the negative 3 moles of OH minus. Okay, so I used the 25 milliliters and the 0.1 molar to get my OH minus. Then I used my 24.9 milliliters, so I did my 0.1 molar times my 0.0249 liters, and I got 2.49 times 10 to the negative 3 moles of H plus. Okay, so then I have to figure out who I have excess of. Well, obviously it's the OH minus, so I just subtract the 2. So remember, it's always largest minus smallest, because you're trying to see what you have left over so that you can get that pH. So once I subtracted, I ended up getting 1 times 10 to the negative 5 moles of OH minus was what I had the excess of, which makes sense because we started with base, we're adding an acid, but we haven't made it to equivalence yet. So I know my pH should be greater than 7. Alright, but remember, I need molarity to plug in. So I have to divide by the total volume. So I added 25 and 24.9. And I got a total volume of 0.0499 liters. Okay, remember this right here is my total volume. And so after I did that, I got 2 times 10 to the negative 4 molar OH minus. So once I have my molarity of OH minus, I can just use my pH square formulas to get to pH. So if I do negative log of that, though, I'm going to get POH. So I do negative log of 2 times 10 to the negative 4. And I ended up getting 3.70, but I don't want POH, I want pH. So pH is of course 14 minus the 3.7, and so I got 10.30, which makes sense because I'm trying to neutralize a base. I haven't neutralized it all the way yet, so my pH should clearly be higher than 7. Alright, so hopefully you got that one right. If you didn't, pause it and maybe try part B real quick, or go back and look at part B and see if you need to fix anything. Alright, so I'll assume you've done that. So now that I have passed equivalence point, so I have added excess acid, I would now expect my pH to be less than 7. Alright, so I start over again. So I'm starting with the 25 milliliters of my base. So this number right here will stay the same. Like this number's not going to change. It's still 2.5 times 10 to the negative 3 moles of OH minus. I don't have to redo that again. But I do have to redo my acid because this time I've added 25.1. So it would be 0.1 molar times 0.0251 liters. And that ended up giving me 2.51 times 10 to the negative 3 moles of H plus. So this time I have excess H plus. So I just subtract 2.51 times 10 to the negative 3 moles of H plus minus 2.5 times 10 to the negative 3 moles of OH minus. So I can see who I have excess of. It's obviously the H plus. And it ends up being 1 times 10 to the negative 5 moles of H plus. But remember, I need to plug into pH square, so I have to have molarity. So I need to divide by the total volume. Okay, that's so important. So many people don't divide by the total. Okay, so I do 25 plus 25.1, which of course gives me 0.0501 liters. And so I end up getting 2 times 10 to the negative 4 molar H plus. But it didn't ask me for concentration of H plus, it asked me for pH. So I just plug in. So pH is negative log of H plus, which is 2 times 10 to the negative 4. And so once I solve, I got 3.70, which again makes sense because I have passed the equivalence point, so I have excess acid, which means my pH should be less than 7. All right, so hopefully you got both of those right. Unfortunately, if you thought those were long, the strong ones are the fast ones. So now let's go to the strong weak. All right, so if we have a weak acid and a strong base, there are still 4 important points. It's the same important points as on strong, it's just we handle them a little differently. So the initial pH, so instead of initially just being able to use the pH squared to get pH, if you start with a weak acid, you need to use Ka. So you would need to set up an ICE chart to figure out pH like we've been doing. All right, in between the initial pH and the equivalence point, the pH is calculated based on the neutralized acid. You will have a buffer, so then you'll be able to use Henderson-Hasselbalch, okay, our saving grace. All right, and then you have the equivalence point. Now remember, if you have a weak acid and a strong base, equivalence point will be greater than 7. If you have a weak base and a strong acid, your pH at the equivalence point will be less than 7. If you have strong, it's 7 exactly. So the equivalence point, the pH is calculated based on the neutralization of the acid. It will be higher than 7 for weak acid, strong base. After the equivalence point, the pH is calculated on the excess base only. All right, so keep in mind, right here, you have a buffer, which we love because we can use Henderson-Hasselbalch. One other important point to point out is the half the equivalence point. So see, I can see that equivalence point is about 25. So halfway there is 12.5. That's when pH equals pKa. All right, so if you're asked at half the equivalence point what the pH is, you don't need to do all this math and ICE charts and all this stuff. You just say, okay, pH equals pKa, and you can plug in negative log of your Ka, and that'll give you your pH. So half the equivalence point is a sweet spot on the weak strong. All right, so let's just go ahead and jump in because we don't have anything else to do but do a whole lot of math today. All right, so it says calculate the pH of a solution formed when 45 milliliters of 0.1 molar NaOH, so I can see I have a strong base, is added to 50 milliliters of 0.1 molar CH3COOH. So this is just another way of writing acetic acid, and so that means I have a weak acid. And then it tells me the Ka is 1.8 times 10 to the negative 5. All right, so in other words, we are not at equivalence point, because see how the concentrations are the same? Equivalence point means I've added equal volumes. Okay, now you don't always add equal volumes to get to equivalence point. It just depends if the molarities are the same or not. Okay, in this case they are. So in other words, we are not at equivalence point yet. We're before equivalence point, so we're in that buffer region. All right, so let's go ahead and get started on this. So first, I gotta still do my neutralization. Okay, so here I have 0.1 molar of my NaOH, which OH is all I care about, times 0.045. And I get 4.5 times 10 to the negative 3 moles of OH minus. Okay, so I'm going to start just like I did for strong. Okay, go ahead and figure out how many moles and who neutralized who. Alright, so then I start with my 0.1 moles of, or molar of my acetic acid, and I multiply it by its volume, so 0.05 liters. So I get 5 times 10 to the negative 3 moles of CH3COOH, or my H plus in this case. It doesn't matter what you want to call it. All right, so now because I'm doing weak strong, I set up my BAAAA chart. Okay, because you can't just do a quick subtraction, because every time an OH reacts with this, we're going to make some conjugate base. Okay, so I got to set up my BAAAA chart. So here is my actual reaction. You know that a lot of times I like to use generics, but usually for the BAAAA chart, I'll write out the actual reaction. Alright, so we have our acetic acid and our base. Remember, the Na is not needed in here. It's a spectator. Our weak acid reacting with our base to make a conjugate base and water. So remember, we have our before addition, addition, after addition. And we don't care about water because it's a pure liquid. Alright, so we start in the beginning. We have 5 times 10 to the negative 3 moles of my acid. In the beginning, I have 0 base, and it did not tell me anything about having the conjugate, so I also have 0 of that. My addition was I added this much base. So this was my addition. But remember, it's going to be used up. Okay? So that means I subtract that much from my acid, but then I add that much to my conjugate base. So since this is used up, I end up with 0 moles of my OH minus. When I subtract here, I get 5 times 10 to the negative 4 moles. And here, I get 4.5 times 10 to the negative 3 moles. So once you see that you have some weak acid and some conjugate base, what should stand out in your mind? Henderson-Hasselbalch. Okay, so Henderson-Hasselbalch, remember, says pH equals pKa plus the log of your conjugate base over your acid, just like that. All right, so normally we need to plug concentrations into here. However, if you don't change these into concentrations, because remember, they'll both be diluted by the same amount. Like in the end, it's both going to be 95 milliliters because it's 50 plus 45, so it'll be 95 milliliters. If you divide both by 0.095, the ratio is still the same. So you can actually just plug moles into this formula. Okay, so I say, all right, well, pH is, remember, P just means negative log. So negative log of my Ka, which is 1.8 times 10 to the negative 5, plus log of my conjugate base, which is 4.5 times 10 to the negative 3 moles, over my acid, which is 5 times 10 to the negative 4 moles. Alright, and like I said, normally for brackets we plug in concentration, but in this case, once we divide both by the same amount of liters, it's just going to cancel out anyway. Alright, and so once I solve all of this, I end up getting that my pH is 5.70. Just like that. Alright, so hopefully that wasn't too bad. Guess we'll find out in a minute, right? Because you're about to try one. Alright. So, you're about to try 2. Alright, maybe pause it and try number 1, and then we'll look at it, and then maybe you can try part B. As far as where I'm going to write all my work, I don't really know, but I'll figure that out. So I'll assume you paused it, and we'll look at it together, and I'll try to find somewhere to write all this stuff. Alright, so it says calculate the pH in a solution formed by adding 10 milliliters of 0.05 NaOH, so I have a strong base, to 40 milliliters of 0.025 benzoic acid. So I know that's not one of my strong acids, so it must be a weak acid. Remember, you got to know your 7 strong acids. And then it tells us that Ka is 6.3 times 10 to the negative 5. So remember, first thing I got to figure out is how many moles of my acid and moles of my base do I have. All right, so I start with 0.05 molar of my OH times 0.01 liters. Okay, so I'm just taking my OH minus 0.05 times 10 milliliters, which is 0.0 liters. So in other words, I have 5 times 10 to the negative 4 moles of my base. And see how even if this is the only part you can get right now and you're struggling with that BAAAA chart, like this is still something, okay? You just got to get this in steps pretty much. So then I look at my acid. So I have 0.025 molar times 0.04 liters. And see, this is one where, finally, we have one, where it's not going to necessarily be the same volume to get to equivalence because my molarities aren't the same. It's actually going to take twice as much of the benzoic acid to reach that equivalence point. All right, so I ended up having 1 times 10 to the negative 3 moles of my benzoic acid. I don't want to say H plus. Let me just write the actual formula because it's weak. So, all right. So next, I got to do my bar chart for my neutralization. So I have my acid, and I have my base, and it's going to react to make the conjugate base and water. And so then I have my before addition, after addition, just like that. All right, so before my addition, I'm starting out with this many moles of my benzoic acid. So I just do 1 times 10 to the negative 3 moles. I start out with 0 of my base. Remember, this is before the addition. It didn't tell me I have any conjugate base, so I'm going to have 0 of that. And of course, I don't care about water because it's a liquid. All right, so the addition itself is the 5 times 10 to the negative 4 moles of base. But remember, that addition is going to be used up, all right, because it's going to react with the acid. So I subtract that much from the acid, all right, and so I end up getting 5 times 10 to the negative 4 moles. Here, because it's used up, I end up with 0, and then I'm going to add that addition to my conjugate base. And I get 5 times 10 to the negative 4 mole. Alright, so once I see, oh, wait a minute, I got weak acid and some conjugate base, that should make me think Henderson-Hasselbalch. Alright, so pH is pKa, which remember just means negative log of Ka, which is 6.3 times 10 to the negative 5, I almost wrote 4, plus log of my conjugate base. Now remember, normally we plug in concentrations, not moles, but we would divide each of them by the same volume, so the ratio remains the same. So I do my 5 times 10 to the negative 4 moles over how much acid, which is also 5 times 10 to the negative 4 moles. And so once I solve that, I ended up getting 4.20, just like that. Alright, so all you do is figure out moles first, set up your bar chart to figure out what you have left over, and then you can plug in the Henderson-Hasselbalch. So it's not that bad. Alright, so if you haven't already paused and tried part B, go ahead and try that. I gave myself less room down here, so I'm actually going to work part B out up here, so don't let that confuse you. Okay, so we already did part A, so we're done with this. Okay, what I'm going to do is I'm going to work out part B right up here. Okay, so I'll assume you've paused it, tried it on your own. It says calculate the pH in a solution formed by adding 10 milliliters of 0.1 molar HCl, so I have a strong acid, to 20 milliliters of 0.1 molar NH3. Remember, I told y'all NH3 is one of the most common weak bases that we'll see. But plus, it's not one of the strong bases, so it has to be a weak base. And then it gave me my Kb value of 1.8 times 10 to the negative 5. Alright, so first, start out the same way. I got to figure out moles of everything first. Okay, so I have 0.1 molar of my acid times 0.01 liters. And so I got 1 times 10 to the negative 3 moles of my H plus, because it's a strong acid, so I know it's fully going to dissociate. Then for my base, I have 0.1 molar NH3 times 0.02 liters. So I have 2 times 10 to the negative 3 moles of my NH3, like that. All right. So for this one, I can see that I have more of my base than my acid. That's what I'm working with here. All right, so I set up my bar chart. So we have NH3 reacting with the H plus to give NH4 plus. So that's my conjugate acid. So we have before addition, addition, after addition. And y'all, you could call this H3O plus and then still add the water, but remember, we don't do anything with the water anyway, so I always try to leave out water whenever I can. All right, so before the addition, we have this 2 times 10 to the negative 3 moles of NH3. We have 0 moles of acid to start with because the acid is the addition. And it didn't tell me I have any of the conjugate acid left yet, so we get that 0 also. All right, the addition itself was this right here. the 1 times 10 to the negative 3 moles. But remember, since that's the addition, that reacts with the base, and so that is used up. So I subtract that much from my base because, of course, that is what is reacting. So I end up having 1 times 10 to the negative 3 moles left of my base. Since my H plus is used up, I have 0 moles left at the end. And then my NH4 positive is, we're going to add that addition to it. So it also becomes 1 times 10 to the negative 3 moles. So if I look, I got a weak acid, that's not a weak acid, a weak base and a conjugate acid, so I have a buffer, which makes me think, of course, Henderson-Hasselbalch. All right, so I use pH. In this case, we're doing base instead of acid, so just everything switches. Instead of pKa, it's pKb, like that. All right, so I do pH, and so it's negative log of my, let's not switch it. Sorry. I don't know what just happened there. We need to switch to Ka. We need to switch to Ka here. All right, did I even write that part out? I did not. Okay, I obviously just switched to Ka in my calculator. So Ka for this ends up being 5.56 times 10 to the negative 10. All right, and so that's what I plugged in. So my 5.56 times 10 to the negative 10. Okay, so y'all remember how to do that. Remember, you do your 1 times 10 to the negative 14 over Kb. And so that's how you get the 5.56 times 10 to the negative 10. That formula is on your formula sheet. All right, and so then I do plus my log of my 1 times 10 to the negative 3 moles over 1 times 10 to the negative 3 moles. Okay, because they both ended up being the same. And so then once I solve, I got that the pH is 9.25, just like that. Okay, so y'all, if they ever give you a Kb, you can switch it over to Ka. All right, not a big deal at all. We've already learned that formula. All right, so let's keep on going. Oh man, I don't know how long this video has been going on, but it seems like forever, and I know we're not even done yet. We haven't even done the super long ones, which is at the equivalence point. Oh, here it comes. Boy, I'm glad I was talking about it. All right, so it says calculate the pH at the equivalence point in the titration of 50 milliliters of 0.1 molar CH3COOH. So I know this is a weak acid because it's not one of my strong ones, with 0.1 molar NaOH. So I have a strong base here. All right, so we got weak, strong. We're looking at the equivalence point. Now notice it didn't tell me what the volume is, but since the molarities are the same, that means it's got to be 50 milliliters. Because remember, the moles have to be the same. All right, so what I start with is figuring out my moles. All right, so we're doing 0.1 molar times 0.05 liters. And so I ended up getting 5 times 10 to the negative 3 moles. And that is of my acid, but that is also of my base. Because remember, we're at equivalence point. So I've added the same amount of moles of each. So I have both of them already. All right, so I do need to switch back over into molarity. No, I don't. I don't know why I said that. Sorry. I did for some reason on here, but then I went back to the other thing. All right, so I need to set up my bar chart. So I have my CH3COOH plus my OH minus yields, of course, my conjugate base and water. So I have my before addition, addition, after addition. So my before addition is I have this many moles of acid. So 5 times 10 to the negative 3 moles. I have 0 of my base because it didn't tell me I had any at the beginning. I have 0 of my conjugate base. And then, of course, I don't care about water. So my addition was this much base because, remember, we're at equivalence, so it's going to be the same. So that's going to be used up. And I'm going to subtract that from my acid. So in this case, y'all notice I actually end up with 0 moles of my weak acid. I end up with 0 moles of my base because that's what was used up. And I add that to my conjugate base. So I have 5 times 10 to the negative 3 moles of my conjugate base. Now this is where it's unfortunate since I don't have some weak acid and conjugate base, I can't use Henderson-Hasselbalch. Equivalence point for weak strong is the worst. Alright, so unfortunately that means now I have to set up an ICE chart. So we do a BAAAA chart and an ICE chart just to figure out the pH at the equivalence point. Alright, so I set up my ICE chart, but remember in an ICE chart we do have to have molarity. Sorry, that's why I misspoke a second ago. Instead I was changing it to molarity. I was, for some reason, glancing down at my ICE chart, which was next on the page instead of at my BAAAA chart. Alright, so I do need to plug in molarity, so that's what I did first, was I changed my moles to molarity. So I said, okay, I have 5 times 10 to the negative 3 moles, and it's in 0.1 liter. Okay, because we have 50 plus 50, so 100. So it's 0.1 liters, so don't forget to use total volume. And so I ended up getting that it's 0.05 molar of my CH3COO minus, just like that. So remember, as much as we want to use Henderson-Hasselbalch here, we can't. So then I set up an ICE chart. So what exactly is this conjugate base going to do? It's going to react with water. Okay, so I have my conjugate base. It's going to react with water, and it's going to make some of that weak acid and some OH minus. Okay, so in other words, like the reaction is just the opposite of my neutralization reaction. See, notice all I did was just switch the reaction around. Okay, so I set up my ICE chart. So initially, I'm starting with what I just decided was 0.05 molar of this. I don't care about water, and it told me I had 0 of these. See, notice I have 0 of those to start with. Now, I don't know how much I'm going to use, so this is where we got to go to our x's again. So it's 0.05 minus x, and then it's x and x. Alright, now the problem is they gave me a Ka, but I didn't set this up for the acid. I set it up for the base. So in other words, what I need to do is I need to figure out my Kb. Okay, so of course to get Kb from Ka, you just do 1 times 10 to the negative 14 divided by Ka. So I just did 1, well here, I'll write it out. I did 1 times 10 to the negative 14, since I didn't write it out on the last slide, I guess in case you forgot what I'm talking about, over 1.8 times 10 to the negative 5. And so I ended up getting 5.56 times 10 to the negative 10. The good thing is, because that number is so small, I can do my assumption and assume that this is just going to be 0.05. Alright, so then I just set it up. So Kb is 5.56 times 10 to the negative 10. That is my weak acid times my base, so squared over the 0.05. So x ends up equaling 5.27 times 10 to the negative 6 molar, and that is for my OH minus. Now that I finally, oh my gosh, now that I finally have OH minus, I can figure out pH. But remember, if you do negative log of this, you're going to get POH. So I put in negative log of this, and I get 5.28, but then I say, okay, well pH is 14 minus that. Don't forget that one last step. My gosh, you'd hate to do all this math and then forget to do 14 minus. Okay, so let's, let's recap real quick. First, I had to figure out how many moles of acid and base I had. They were equal because I'm at equivalence point. I set up my BAAAA chart where I showed what I had left. Unfortunately, I only had conjugate base left. I did not have weak acid and conjugate base, so I couldn't do Henderson-Hasselbalch. So then I converted what I had left of my conjugate base into molarity so that then I could use my ICE chart. So I set up my reaction. So again, the reaction was just the opposite because some of this conjugate base is going to react with water to go back and form that OH minus. Alright, so I have my conjugate base floating around. So then I set up my ICE chart. Since I was working with the conjugate base, I had to use Kb instead of Ka. That's another common mistake, is to forget to change it. If I was working with the weak acid, I could have used the Ka value. I did my assumption. I solved for my molarity of OH minus, and then from there I could get my pH. So see, it's only like 1,000 minutes of work. Not a big deal at all. So in other words, will you likely ever see one of these on the AP exam? I doubt it. Because, I mean, my gosh, it would take so long to get to it. Oh, and then you get to try 2 of them. Isn't that fantastic? See, this is what I'm saying. This video, I just keep giving and giving, and you know, you probably don't even want to take it, but you don't have a choice. You got to learn this stuff. All right, so maybe try the first one. I'll assume you've done that. We'll look at it together. I may have to kind of erase as I go this time because I did not leave myself a lot of room to work it out. All right, so it says calculate the pH at the equivalence point when 40 milliliters of 0.025 molar benzoic acid. Okay, that's not one of my strongs. That's a weak acid. Gosh, if only it was strong, if it said calculate pH at equivalence point, it would just be 7. We wouldn't have to do any math. It gave me the Ka right here. Is titrated with 0.05 molar NaOH, which is a strong base. All right, so yours actually has a little trick to it. So if you struggle with this one, maybe watch me do this one and then try the bottom one. Yours has a little trick to it because you're not necessarily just going to add 40 milliliters because the concentrations are no longer the same. This concentration is twice as much, so I only need half as much to get to equivalence point. So what that means is at equivalence point, I only need 20 milliliters of this NaOH. All right, so first thing we got to do is figure out how many moles of each we have. All right, so I have 0.025 molar times my 0.04 liters, and that gives me 1 times 10 to the negative 3 moles of my acid. But remember, we're at equivalence point, so that is also how many moles of my base. Because if you do 0.05 times 0.02, you're going to get the same number. All right, so I got that. So now I got to set up my BAAAA chart first. Okay, and remember, for BAAAA chart, we can plug in moles, so we don't need to change to molarity. All right, so I've got my acid. I'm reacting it with my base. I'm making the conjugate base and water. So I have my before addition, addition, after addition. So before my addition, I have that much of my acid, 1 times 10 to the negative 3 moles. I have 0 of my base to start with. It didn't say anything about having conjugate base, and of course my water we don't care about. So my addition is 1 times 10 to the negative 3 moles of OH, but remember that's going to be used up. All right, so I subtract that much from my acid. So I end up with 0 moles of my acid. Because this is used up, I end up with 0 moles of my base. And then I add this much to my conjugate base. So I have 1 times 10 to the negative 3 moles of my conjugate base. So again, we cannot just use Henderson-Hasselbalch, which would be fantastic. That's why we love that equation so much. Because then I just pop it in there, get it, and move on with my life. But I can't. Okay, so I'm going to go back and erase this now. Okay, because I need to set up an ICE chart to figure out what's going on with this right here. All right, so I'm going to erase and just kind of work back and forth today. All right, for an ICE chart, I have to have molarity. I can't have moles. So I take my 1 times 10 to the negative 3 moles of my conjugate base, and I divide by the total volume. Okay, so we've added 20 and 40, so that's 60 milliliters total. So I divide by 0.06 liters, and I get 0.017 molarity of that conjugate base. Okay, so now I'm ready to set up my ICE chart. So remember, my ICE chart is just going to be the backwards reaction of this. Okay, so I have my C6H5COO minus reacting with water to form my acid and my OH minus. Alright, so I set up my ICE chart. So initially I have this 0.017 molar. I don't care about water. Initially I have 0 of both of these. Okay, so 0 for both of these. So I subtract my X, add my X, add my X. Alright, so I'm ready to set it up, but the problem is, of course, I've set up the base reaction, not the acid. It gave me Ka, so I'm going to need to switch that over to Kb. Alright, so, sorry, now I'm going to erase this side so I can continue over here. Alright, so to get Kb, I just do 1 times 10 to the negative 14 divided by Ka, which is 6.3 times 10 to the negative 5. So for Kb, I ended up getting 1.59 times 10 to the negative 10. So I can assume, thank goodness. Gosh, if we also couldn't assume, I would just have to stop the video, y'all, at this point. All right, so we're ready to plug in. So we say, okay, KB equals my acid times my base, because remember, it's just products of reactants, over the 0.017. So once I solve, X ends up being, my gosh, there's so much work on my paper, I have trouble even finding where I'm looking. 1.64 times 10 to the negative 6 molar, that's for my OH minus. But we want pH, so you got to keep in mind, if you do negative log of that number, you're going to get POH, you're not going to get pH. So once I do negative log of that, I got 5.79, and so last step is pH is 14 minus that. And so that gives me 8.21. So the extra trick on this one, besides the fact that the whole thing is tricky because it's horrible, is that you did not need 40 milliliters of this to reach equivalence. Okay, remember, equivalence is when the moles equals the moles. So the fact that this molarity was twice as much means I only need half the volume. All right, so if you either tried that one, maybe didn't do so well, or you got it, or you waited on me to show you a second one, try this bottom one. Okay, so because I gave myself literally no room, I'm going to work it out in kind of the same spot. All right, so let's look at this one together. I'll assume you've already tried it and you did fantastically. So it says we have 40 milliliters of 0.1 molar NH3, so that is a weak base. And it's titrated with 0.1 molar HCl, so that's a weak acid. So see, this time my molarities are the same, so at equivalence point it would be the same volume. So I have 40 milliliters of my HCl also. All right, and then they gave me KB is 1.8 times 10 to the negative 5. All right, so first step, remember, is to get the moles. So I start with my 0.1 molar times my 0.4 liters, and I get 4 times 10 to the negative 3 moles.
Coach Bear, Coach Tollefson, please come to the front office. Coach Bear and Coach Tollefson, please come to the front office.
And remember, because we're at equivalence, the moles are equal. So that's of my weak base and my H plus from the HCl. All right, so then I'm ready to set up my BAAAA chart. Okay, so I have NH3 plus H plus yields NH4 plus. So we have before addition, addition, after addition. Okay, so remember, you could have put H3O plus if you want and then plus water, but we don't use water anyway, so it doesn't really matter. All right, so how much of my NH3 am I starting with? Well, I'm starting with 4 times 10 to the negative 3 moles. I didn't start with any acid, and it didn't say anything about starting with conjugate base. Remember, conjugate acid. It'll tell you in there if you're starting with something else. My addition was this much of my acid, but that's used up. So I subtract it from my original weak base, so I get 0 of my weak base left. Because the H plus is used up, I have 0 of that left, and then I add that amount to my conjugate acid. So I get 4 times 10 to the negative 3 moles. All right, unfortunately, again, I don't have weak acid and weak base and conjugate acid, so I can't use Henderson-Hassel law. So I got to set up ICE chart. But remember, for ICE chart, we need molarity, not moles. So I do my 4 times 10 to the negative 3 moles, and I divide by the total volume. So notice I did 40 and 40. So that's, of course, 80, which is 0.08 liters. And so I ended up getting 0.05 molar NH4 positive. But now, I'm so lucky I get to set up an ICE chart. Because if I didn't enjoy doing all of this enough, I just needed to do it even more. All right. Oh my gosh, I just realized on my paper, this is the last exercise, thank goodness. Okay, I'm not going to lie to you, I'm getting kind of tired. All right, so remember, we just set up the reverse reaction. So don't let the reactions throw you off. Like, this was neutralization, and if we have some products, some of it will shift back, so it's just the opposite reaction. So I set up my ICE chart. So I'm starting with the 0.05 molar of my NH4. I'm starting with 0 of both of these because I said on my BAAAA chart I had 0. So then I subtract X, add X, so I get 0.05 minus X, X and X. Alright, so set up my chart. Now the problem is, they gave me KB, but now I'm working with the conjugate acid, so I actually need Ka. So here I'm going to erase my BAAAA chart so that I can deal with that thing. Okay, so to get Ka, I just do 1 times 10 to the negative 14 divided by my Kb, 1.8 times 10 to the negative 5. So for Ka, I ended up getting 5.56 times 10 to the negative 10. And so, of course, I can assume again, which is fantastic. We don't want to do any, gosh, I mean, could you even imagine also doing quadratic formula? Like, it would just be ridiculous. So then we just set up our values. So Ka, which is 5.56 times 10 to the negative 10, equals my products, which is just x squared, over my reactant, which is 0.05. So my x ends up being 5.27 times 10 to the negative 6 molar, and that is, of course, my H plus this time. So since it's my H plus, to get pH, I just do negative log of that. I don't have to do the whole, oh, I calculated pOH first. All right, so I plug all that in, and so I got 5.28. So hopefully you got that one right. If not, like I said, I doubt they will ever ask you equivalence point, like to calculate the actual pH. And they might ask you, is it going to be greater than or less than 7, but you should be able to predict that based on it's a weak acid, strong base, or a weak base and strong acid. But like to have you actually calculate the number like that, I highly doubt that will be on there just because of how long it would take, because the test is, of course, time. All right, so some last things we have to talk about is how does the curve change based on, are you having a weak acid and a strong base, a weak base and a strong acid, who's titrating who, what happens as one of them gets weaker. So this is what it would look like if you had strong acid. You'll start very low, you will have this nice perfect S, and equivalence point will be at exactly 7. All right, and you'll have this nice perfect S. That's what it looks like if you titrate a strong acid with a strong base. As the acid gets weaker, notice the bottom part of the S becomes less and less perfect. Okay, the top part, notice, remains the same. As it gets weaker, the vertical portion gets shorter, and your pH at equivalence gets higher, because the weaker the acid, the more conjugate base, the stronger the conjugate base. And then remember, at half the equivalence point, your pH equals your pKa. So sometimes they might ask you like, oh, you want a buffer of this pH. Which one would you pick? So you want the pH to equal the pKa as best you can. All right, the opposite happens for bases. If you have a base being titrated with an acid, if it's a strong base, again, you get this perfect S. All right, it starts with a high pH, and of course it goes down as you titrate. pH at equivalence point is exactly 7 for strong. The weaker the base, notice again, it messes up the initial part of the S, where it's just not as much. So the vertical portion gets shorter as the base is weaker, and the pH gets lower and lower than 7 as it gets weaker. But the end of the curve does not change, because that's still based on just your strong acid. And then again, at half the equivalence point, because we're talking about base now, your pKb equals your pH. So there are 3 main differences in a strong acid, strong base titration and a weak acid, strong base titration. The weak acid has a higher initial pH than the strong acid as long as the concentration is the same. A weak acid has a smaller, sharp slope than a strong acid. What that's talking about is this thing happening here. Okay, see how weak it's not as perfect? All right, and then the pH at the equivalence point is above 7 for a weak acid and equals 7 for strong. Okay, so it's 7 for the strong, which is the purple, but for the black line, which is your weak, it's above 7 because of that conjugate base. All right, and then last thing we have to talk about, thank goodness, I'm interested to see how long this video is, because I feel like I've been talking for 3 hours now. I'm surprised my camera hasn't run out of memory. All right, so the titration curve for our polyprotic acid has an equivalence point for each hydrogen removed. Okay, so for example, here we have one equivalence point for one hydrogen removed, and then here we have a second equivalence point. So for example, this acid could be H2SO4, and so this would be the equivalence point for the one H removed, and this would be the equivalence point for the other H removed. All right, and so for polyprotic acids, we usually don't see them ask you any calculations on it, just because a lot of times you can kind of discount the second hydrogen anyway, because remember how we previously talked about, as long as the Ka's are at least 10 to the 3 difference, then you really only have to focus on the first one. Alright, so hopefully if you haven't been scared off by equilibrium by now, this video finally did it. But you know what? We still got some more videos, so you're just going to have to pull it together and make it through the last two.